Hello everyone, I was recording this video and my phone glitched out and now I need to rush through it. I don't know why it stopped recording, but let's hope that doesn't happen again. So today we're going to be going over exponential differential equations as opposed to logistic, which will be the next video. And exponential differential equations are going to be equations that are defined as one or two things. Either a population that grows uncontrollably, like an invasive species, or something that grows with what we call continuous or compounding interest. So when you're talking about money, almost always when you're asked to model compounding interest, and you're going to rate, you're almost always going to be using E. And E is the key to our exponential differential equations. So I'm just going to start off with a quick example, and that's really going to be more or less it, because when you see these equations, they're almost always going to end up in some sort of way that looks either like this, or maybe even like this, and maybe even having a plus c or plus some other value at the end, right? And these are the two ways that they're going to present themselves. Either way, you may or may not have a constant that you add to it. You may have the constant up here. You may have something multiplied by it, and then you're going to have a rate and a time, and that rate is going to govern how much your value increases over a period of time. So that being said, sometimes what you might even see is something like this, which is where this is your original value multiplied by all of these things, because the rate over time, the rate and time are going to multiply this initial value. Because when you compound something, it's going to double, triple, etc. over this set period of time. So that rate is going to change this value, which is going to increase this value over a set period of time. All right. So what you usually see in differential equations is this, and I'm going to start off with our example. dy over dx, which is the rate of growth or the rate of change, or our derivative, is equal to, in this case, it's negative 5y. Right, so this is negative 5, our original function, which we're trying to get. And then we're given an initial condition that we need to satisfy. So y equals 4. And x equals 0 is our original condition here. Sometimes it might say f of 0 is equal to 4, which is most likely because the College Board likes to talk in terms of f of blank, because that makes things a lot simpler. Function of. So keep an eye out for that. But these are basically the same thing. Okay, so dy over dx is equal to negative 5y. If you guys don't recognize this already, when you have y, or your function, in your equation, when you have your derivative, this essentially means that you're going to have to do perform some sort of implicit differentiation, right? Okay, so that's what we're going to do when we're trying to get this original equation. So dy over dx, we're going to move this so that all the y stuff is on one side and all the x stuff is on the other side. So I'm going to multiply both sides by dx, which essentially does this, 5y dx, and divide both sides by negative 5y. So we get this. 1 over negative 5y is equal to dx. And then I integrate both sides. Integral of dx is just going to be something simple, which is just going to be 1 times dx. Okay, this is 1 times dx. So if 1 times dx is what we're integrating, we're going to get something simple like x, because the integral of the derivative of x is just x, right? And now, when you have two integrals, one on each side of the equation, you could add the plus c on either side. I'm just going to add it on this side because it's a lot simpler, and ultimately this is going to be something with y equal to this. So it makes sense to have the c on this side. And so now that when I integrate this, this is just, I'll move this to the outside. We have 1 over negative 5. And then this, integrated, this is 1 over y, or 1 over a value. It's just going to be natural log of the absolute value of that value. Natural log of absolute value of y. Cool. And then you have still that 1 over negative 5. So I'll multiply both sides by negative 5 to get rid of this, and to get negative 5 over here. So we essentially have negative 5 times x plus c. Cool beans. All right. Now what we can do is say, okay, there's an interesting thing going on. Natural log of y is equal to this. How are we going to make sure that we solve this in terms of y? We don't want the natural log here. Well, what we can do is simply this. Natural log, if you guys don't remember, is log based e of this. So what this means is that e to the power of this is equal to this. Again, e to the power of this stuff is equal to this thing. So that means that I can rearrange it so that I say e to the power, and there's the e, of negative 5x plus or minus 5c, and this technically is just c because c is any number that we want it to be, is equal to y. And now we don't really have to worry about absolute value because this is always going to be positive. E to the value of whatever is always going to be positive. I could raise something to the power of negative 1, and that doesn't make it negative, that just inverts it. I can make something to the power of negative 100, and e to the power of negative 100 is not a negative number, it's just 1 over e to the 100. That's what that is. So it's never going to be a negative number, so we don't have to worry about that absolute value sign. So y is equal to e to the power of negative 5x plus c, and what is that plus c? Well, we can figure that out in actually a very simple manner. So when you have things added in your exponent, you remember that you can split them up like this. E to the negative 5x multiplied by e to the c is the same as this thing. Because when you add these two things together, given they have the same base, when you multiply these two things together, if they have the same base, you add the exponents. So you can split them up so that they're multiplied each with these individual exponents. Cool. All right, and we can figure out what c is going to be based on, that's right, our initial condition, where x is equal to 0 and y is equal to 4. So if I get rid of this weird thing, if x is equal to 0 here, that means that 0 times 5 is just 0. So e to the 0 is just 1. So y is equal to e to the c. So 4 is equal to e to the c. Well, if I do natural log here, I could say that the natural log of the absolute value of 4 is equal to c. And all in all, that's going to be more or less it. But there's more. There's more than that, actually. One last thing that I can do. So c is equal to the natural log of 4. So the last thing that I can do is say e to the power of negative 5x times e to the power of now natural log of 4. Remember what natural log is. Natural log says that e to the power of this, of the natural log, is equal to 4. So if I raise e to whatever the natural log of 4 is, whatever this is equal to, it will equal 4. So that means that what I can do is just remove this and put it in front. And that is our final differential equation. That is the solution to our problem. Yeah, so I hope everyone enjoyed that. I hope that helps, and I hope that you do well on the AP exam. Yeah, stay strong.